second session of the Real World MPC workshop. And right now I would like to welcome, I want to say this is on threshold post-quantum signatures. Very excited to hear this part of the event. And right now I would like to welcome Giacomo Borin, who will tell us about parrots, I don't know how to, parrots, what isogenies can offer for the NIST threshold call. So it's 20 minutes and 2 minutes for questions, and please. Okay, so please take ahead.
Thanks. Uh, I, I am Giacomo Borin from IBM Research and University of Zurich. Today, I would like to present this joint work with a lot of other researchers in isogeny-based cryptography and more in general in distributed cryptography about the threshold scheme from isogeny-based assumptions. The motivation for this work and this submission is the general interest in threshold schemes, in particular in post-quantum threshold scheme, sparkled by the recent NIST call and more in general by the post-quantum transition. And one of the interesting things about this field is that it still lacks maturity, and like we are designing scheme at the same time on which they get like standardized and started to be used. And one question we are trying to answer is to understand like if isogenies and how can be used for threshold cryptography. I guess not of you knows about isogenies, and some of you may have like a partial knowledge. I won't go deep into details, but I would like to give like just a flavor and ideas on what we are speaking about. And isogenies are a complementary, let's say, family of assumptions with respect to lattices to be used for post-quantum cryptography. There are different kinds of schemes that can be derived from isogenies, and they can be divided in two kinds of schemes. The one, let's say, more generic, just relying on supersingulated curve, like Psyche or ski sign, and one, let's say, that relies on a kind of different assumption that are framed as isogeny group action, that are, let's say, easier to understand, but relatively harder to instantiate. And recently, some of you may know about this pivotal event, the attack on Psyche, that broke one of the main schemes of isogeny-based cryptography. This, first of all, didn't broke all the other schemes. So in particular, the one relying on this isogeny group action framework were not broken, like their security were not, let's say, changed by this attack, since they are complementary assumption. And more importantly, thanks to the idea from this attack, as it happened for other schemes, it were actually possible to solve a long-lasting problem for isogeny-based group action that were their instantiation. So we have to assume that until like 2 years ago, we didn't even know if it were possible in principle to instantiate these schemes from isogeny-based group action. So we were in a strange situation in which we know a lot of potential schemes, in particular threshold schemes, that could like actually be like written and you can give specification, but we lacked like the actual like mathematics machinery to instantiate them in practice. And thanks to recent development, we actually like discovered this to be doable, not only like from a theoretical point of view, but like practically, concretely, how to write algorithm to implement this algorithm. And this was just in time for being able for this threshold call to actually provide some isogeny-based algorithms. So to be more precise, to go more into details about the schemes that can be instantiated using using isogeny, and then we plan to provide in this package submission when speaking about a threshold signature, Macau, that feature like a expensive pre-processing procedure, but then a more faster online signing operation, and with the possibility of eventually tracing misbehaving user with some identifiable abort protocol. Then a public key encryption that essentially rely on an I key that is one of the main, let's say, byproduct of isogeny-based group action with the distributed decapsulation procedure. And then eventually these two schemes can be augmented with a distributed key generation procedure. And the advantages of designing scheme in this way is, first of all, the quantum safety with an assumption that is complementary to lattice. It's fair to say that they are quite independent. So if one of them get broken or severely, let's say, attacked, the other one is not expected to be broken using the same algorithm. And also they can provide different trade-offs when you try to instantiate them. And particularly, isogenies usually tends to be smaller than lattices. However, when we speak about isogeny-based group action, there are a few disadvantages. First of all, that they have a quantum sub-exponential attack. That this means that we really need to look closely at the parameters when we need to instantiate them. And they are less efficient with respect to other isogeny-based schemes, for example, like SkiSign. And another interesting advantages of this kind of assumption is that they have a generic isogeny agnostic framework that can be used to describe them. They make it easier to understand. You don't really need to understand isogenies when you are working with this kind of schemes. And under this framework is the same framework that you can use to understand the more well-known elliptic-curve cryptography. However, in the post-quantum scenario, there comes some important limitation in using this framework that I will touch on now. And this framework I was referring to is the group action framework. The idea is to generalize the exponentiation operation from classical cryptography. So you have a group acting over a set with some, let's say, with a function that satisfies some additional properties. And the difference between what we did in classical cryptography and what we do now in post-quantum cryptography is that while before, once you have like some kind of shared secret between parties, they can apply the classical, let's say, exponentiation operation and then publicly combine the result. While this is not possible anymore when you are like in the group action scenario, and this is like kind of equivalent to requesting that the action is not broken by a quantum computer, so it's actually like a strong requirement. And instead, you have to apply these actions sequentially. An interesting question would be actually for, like you're constrained to this limit only if you are not willing to look into the computation of the group action. So an interesting question would be, what if we actually try to look into the computation and apply some more general multi-party or more advanced multi-party computation techniques and try to solve this limitation and compute like this operation without relying on the general framework. However, if we have, like coming back to what we are working now, if we are in this framework, what it means to apply an action, it means that we have to perform some sequential operation. And this is operation that need to perform it during the decapsulation or the signature preprocessing. And the idea is that whenever, like, let's say 3 users need to apply their shared secret over some kind of set element, they would need first the initial user to apply his secret, then broadcast it to the other users, in particular to the second user that will take this element and apply his some kind of secret operation depending on his shared secret that will broadcast it again, and then send it to the last user that will apply again his secret, and then they will get at the end the application of the secret element. If they need to verify this operation, one option would be to use non-interactive technology proofs, but these are relatively expensive, still doable in practice, but we want to, let's say, use them with care. Otherwise, it's still possible for users to interact between themselves using interactive proofs and show to the rest of the pool of users that they acted honestly. And the advantage of this kind of proof is not only that they are, let's say, more efficient with respect to non-interactive technology proofs, but they can be efficiently parallelized. Okay, so let me briefly explain what they meant when they spoke about the problem with the quantum security. The problem is that, like, let's say, this field is relatively new, and sorry, not this field, but these new schemes are relatively new. So, like, when you have some kind of sub-exponential attack, think, for example, about RSA with number field sieve, and you need to fix parameters, you really need to do it having some concrete estimates about the cost. And, like, to tell it simply, the reason is that we cannot fully agree as of now in the community what's the actual cost of computing, like, an isogeny on a quantum computer. However, we're working on that. It will require a few months, and part of the people that I listed before are actually, like, providing tools to perform this computation in a way that is, say, agreeable by everyone, and came up with precise parameters. As of now, to still be able to get an idea about the efficiency, we're considering three possible parameter choices. One that is the more optimist one, the smallest we can opt for, the more efficient we can opt for. One that is the worst possible one, on which we are, let's say, sure to be quantum secure, and an intermediate one that will serve as a reference point. And fixing these three possible parameter choice, we can have an idea on how efficient this scheme can be. For the preprocessing of the signature, we are in the order of seconds, while for the threshold public key decryption, we are in the order of milliseconds. Also, like, the online phase for the threshold signing will be in the order of milliseconds. It can be thought to be equivalent to Sparkle in some sense, in which you have to perform some randomness opening plus some scalar operation. And then the distributed key generation, that is actually the most expensive operation, will require time in the order of minutes. And this is all because we need to perform this costly non-interactive technology approach. And with respect to the sizes, these are the expected sizes. We expect to get something actually smaller at the end, because we have discovered some more efficient compression techniques. However, these are fair estimates on what we can get. And this is for the signature sizes, is plotted the public key versus the signature. With respect to the encryption, we can get something even better, staying in the order of 1.5 kilobytes, even in the worst case of having to use the biggest possible parameters, the safest parameter. And to give some details, so let me close by giving some details about how the schemes would be eventually deployed, if considered. For the threshold, the idea is to have similar to Sparkle, commitment generation phase, and then, like, a broadcast of the responses. This first construction would be, say, working, but only passively secure. If you want something actively secure, as we wish in practice, you need to add some interactive proofs and some randomness generation phase at the start of the signing procedure, online signing procedure. And this part, the computation of the group action plus the interactive proof is actually the more expensive part, but it can be preprocessed, while the online phases is just some broadcasting of randomness and responses. And eventually, if something goes wrong during the computation, it's possible to perform some checks with non-interacting technology proofs and check which of the users performed like cheated during the protocol. With respect to the threshold decryption, what we have to do is essentially the classical Elgamal-like encryption, but performed with group actions, in which you need to add, as for Elgamal, some kind of non-interacting technology proofs. If we are in the exogenous scenario, we can do it using some compact non-interacting technology proofs. And then we need to perform the decapsulation that this time needs to be sequential because it really needs to compute one group action. And you need to combine some sequential group action with interactive proofs. And eventually, if some of one of the user cheat and like make the decryption phase, you can still check them, check who was the one who cheated using non-interacting technology proofs. An alternative approach, if we don't care about the ciphertext being too small, could be to just essentially concatenate a certain number of ciphertext. This is an option that, since we like the single ciphertext would be really small, we are considering. It has some nice properties, but some drawbacks, in particular like the linear times during the encryption and the linear sizes during in the ciphertext. And we would like to get feedbacks from people to understand if there are some scenarios in which this in practice can be relevant, since like the only other options for as of now for threshold decryption is in the order of 30 kilobytes, even for the smallest possible parameter sets. And then there is the distributed key generation. This one is more of a feasibility. Sorry. As of now, the results show that this is feasible in practice, but it still requires operation that require minutes to execute, because you have to perform a lot of non-interacting technology proofs. It would be an interesting question if it's possible maybe to, since it is a really specific operation to perform this using just MPC, and I would be happy to discuss this if someone is interested. Okay, so let me close by highlighting what will be like the next move for this submission. The idea is to give like a specification of the schemes that is as easy as possible to understand, just relying on the abstraction that I given before on group action, and eventually even give like potential an implementation that is easy to read using Python, and Python or some kind of high-level language like Golang, and then only have like an optimized implementation for the actual costly operation that are like the exogeny-based operation, and for them using some assembly optimized or pure C implementation. And then also a report on the quantum security of the assumption. Thanks for the attention.
Okay, so we have definitely time for questions. Do we have questions for Giacomo here? Please.
Thanks for the talk. You briefly mentioned at one point an idea to do signature compression. All right, we're all awake now. Yeah, you briefly mentioned the ability to do compression of signatures by a third. Can you kind of briefly maybe outline how that would work, or is there like not time for that?
I don't know, how much do you know about class groups? Okay, well, class groups are, let's say, an alternative to ellipticals that are used by some kind of I know that they're using blockchain for this verifiable reliable function, and usually there is like a standard way to compress them that we thought to be the more efficient one. But looking at what like at the actual like object that are the same one that we need to use in isogeny-based cryptography. We noticed that by remembering that these are like isogeny-related stuff, essentially, if you just look at it just as a class group element, you would perform a lattice reduction and be happy with that. But if you look at it as an isogeny, what you would do, you would search for the shortest equivalent isogenies of prime degree. And this is a relatively easy operation. And when you do that, you actually are able to compress it to the minimum information theoretically bound you have on that. That is like square root of the prime size. And yeah, like we just noticed that while implementing the stuff that this was possible, and so you can apply to compress a bit the representation cost of the class group.
Okay, we have time for one more question.
Hello. This is not quite related to the talk, but I'm curious if you know of any progress on threshold schemes for supersingular based like ski sign type systems that aren't based on group actions, but rather just kind of generic isogeny approaches.
We have been trying to work on that. Like if the goal is just to get some kind of short signature, we already have like a project on that. It's a more theoretical project as of now, and it would rely on Prism, that is, let's say, an alternative to ski sign that is easier to thresholdize. And on that, you could actually get some kind of, let's say, threshold signature with between 200 and 300 bytes of size. If instead the goal is actually to get a ski sign version, like a full ski sign as it is submitted to the threshold call, this would be a little more difficult because like it really relies on some kind of, let's say, like the computation you would like to thresholdize will leak immediately the secret if you see even like a small part of them. So you really would need to use MPC for all, let's say, all the part of the protocol. We tried to look into that, but it doesn't look so simple because of like, also you need to convert between like rational integers and finite fields. Okay, theoretically feasible, in practice we see it more difficult. So probably it's easier to change the scheme if the goal is to get like a, actually like 200 byte signature.
Okay, so let's thank Giacomo again.